Hi, Anand and Nicholas and Shania. I think you're old hands at this. Hi, Abigail. Hi, Christina. I think actually if there's just a number of people, you tend to get kicked out quicker, although yesterday nobody was kicked out. Okay, right. I think everybody's back, or at least I hope so. I'm sorry about that. Okay, what I want to do today, last term we looked at organic chemistry, but we looked in terms of the functional group. So what is an alcohol, what is an alkene, what is an alkyne, and so on. Now I want to move on to the reactions. So what influence does that triple bond have in an alkyne? What influence does that OH have? So the first thing I want you to think of, though, is 4 tips for organic reactions, because organic reactions do work differently to what you've used to so far. Who has done the CH2000 standard on recognizing ions? You know, where you mix 2 substances together to see if you've got a precipitate or if something dissolves. Has anybody here done that? So see guest is typing. We don't offer it because it's very practically based, but if you've done a bit of it at school already, then you may have. It's a great standard, lovely chemistry in it, but you would have noticed that things happen pretty much instantly. You mix 2 solutions together and you get a precipitate, and then you mix, add an acid or whatever else, and then the precipitate disappears. It's pretty instant. You don't have to heat it. Organic chemistry is different. The reason being is, as I've got here, is you've got to break covalent bonds. Now, covalent bonds are strong, so you're going to need lots of energy to break it. So it's not just going to snap like that. Ionic bonds are also strong. Remember your 2.4 standard we did last term. Both of these types of bonds are strong. The difference is in your solution of ions, your ions have already been separated when you dissolved that ionic compound in water. So if I took salt like sodium chloride and I mix it in water, the energy is going to be involved in breaking those ionic bonds there when the water molecules extract each ion out. Okay, and they can only do that because of those strong bonds, attractions formed between the water and the ions. With your organic reactions, we don't really do them in water, and there's not much attraction between a non-polar substance and water. So what I'm trying to say is organic reactions are slow, so you have to usually heat them. But with heating, remember I said they're often non-polar, which means they've got low melting points, and so we've got the problem of stuff evaporating. Also, what we have a problem with is that organic compounds tend to be flammable. Just as a question, what does inflammable mean? Does it mean that it does burn easily or it doesn't burn easily? It's a bit of a trick question. It does burn, correct. So if you see a big notice on something saying inflammable, it means it burns. Because I think a lot of people think, oh, it's flammable, so the opposite is inflammable. But if you see a signpost saying inflammable, then it will burn. So we've got to make sure we don't have like Bunsen burners coming into contact with the organic liquids, because otherwise you're going to start a fire in the classroom or wherever you are in the laboratory, which you don't want. So we often have water baths just to separate out, to keep the Bunsen flame, the naked flame, away from the substance we're heating, or we have a heating mantle. Now I'll show you all these things so that these magnetic stirrer bars, anti-bumping granules, will see that. Okay, so here's some of this equipment that I was talking about. Notice I don't have a naked flame here because I'm using a heating mantle. So we're using electricity to heat this up. This says a magnetic stir plate because what we have to stir our solution, because you can't, if you're dissolving salt in water, you can stir it with a stirrer bar. You can't in a substance situation like this. So we tend to put a little a magnet that's sealed in plastic. We put that inside the flask, and there's just simply a magnet around here that goes round and round and round that makes the magnet inside the glass vessel go round and round. So it's a way of stirring it. Then we have to heat. Now, this setup is done to try and remove a substance. So when I'm heating, it evaporates and goes through here, this gas. The gas starts condensing in this cold area here, and then it drips out on the other side. So this is what we call a distillation setup. When we want to separate something out, we want to purify it. If we've got a mixture of stuff here and we want to send it out. Why I'm pointing this out is in the exams, they do expect you to have done some organic reactions. And of course, with the correspondence, we can't do it because we can't send liquids in the post. And these are quite fragile pieces of equipment. So you're going to need to watch the videos. Okay, so here are some videos. Now I'm going to run these both at the same time. Okay, look for J.H.U. Adams on YouTube, or David Reed. This is the other one down here, sorry, David Reed. It's a distillation. Both of these will show you what a distillation looks like. So here they're showing you how you connect all those bits of glassware, and here it's showing it's connected, and they explain what's happening. Those are, remember I said those boiling, anti-boiling granules, you put those in, so it just, instead of it heating in one big thing and it perhaps exploding out, it just makes it burn a lot more easily. Who's ever had like cooked porridge on the stove and then suddenly this bubble comes up and splashes everywhere? Or I suppose people just use muesli or cereals now. Has anybody cooked porridge before? No? Okay, silence. But sometimes if you cook, say, a thick soup or a porridge, you'll find, you know, it comes and splashes everywhere. So that's what those anti-bumping granules are trying to prevent. Okay, I'm not going to carry on further over here. And don't worry about this, what I've said here, this example, because you're not going to be needing it for level 2. Okay, here's another one. This is when I'm not trying to separate something out. So again, this is David Reed, and it's explaining how to do a reflux. If I'm trying to react something, remember we've got a slow reaction. So instead of taking 2 seconds, it's going to take us half an hour. So we've got to heat for half an hour. And we don't want the substance all to evaporate, because remember, organic substances tend to be low boiling, so they'll boil easily. So what we do now, instead of making that place where they condense going sideways, as in the distillation setup, can you see we're making it vertical? And when you set it up, you'll see that when he's adding the anti-bumping granules again, he's explaining about that at the moment. When you set it up, your substance heats up, it evaporates, it will come up here, get into this cool area, and then come down because it's condensed and drip back again. So any questions between about a distillation setup and a reflux setup? So reflux just simply means something is evaporating and then it's condensing down again. So it's mixing with the reaction mixture again, then it evaporates and then it condenses down again. Distillation is what we use if we want to purify something or remove something from the reaction mixture. Okay, so this is, I've said it's boiling away, and the anti-bumping granules is making it boil easily. And can you see that liquid dropping back in again there? So that's how, and we can just Keep on heating it for about half an hour and then until the reaction's finished. Okay, now that you've got your substance, there's often a mixture, and sometimes we've got aqueous together with the organic layer. So can you see my two layers here? This is what's called a separating flask, and it can be used in a number of different ways. For level 2, I don't think it's that important. You will need to go into it in level 3. If you want to watch the video, it's again, look for David Reed. He's got some lovely organic experiments explaining the different equipment. Okay, so that was the first two tips. Organic reactions are slow, and then the specialized equipment. So we looked at how we set up a reflux, this distillation, and that separating funnel, which is not really that important for level 2. What is important for level 2 is that you classify your reactions, and you'll find there are a few different types. The first one is addition. Now, addition is when you're adding atoms or groups of atoms to the compound. So we have to go from, if we have a carbon atom, okay, let me ask it another way. What is the maximum number of bonds that carbon can form? 4, correct. And in fact, it always must have 4 bonds, because if it doesn't have 4 bonds, you've done something wrong. The other thing we can look at it is, if it can form 4 bonds, what is the maximum number of atoms it can bond with? So if you think of carbon forming the 4 bonds, it will bond to 4 different atoms. So that's the maximum. And if it can bond to those 4, it's what we call saturated. We can't add any more atoms because we can't form a 5th bond, so we can't add a 5th atom. But we can have, in alkenes, we can have 4 bonds, but where each carbon is only bonded to 3 atoms because we have a double bond. Or actually, addition happens in alkynes. I didn't put it here, but it can also happen to alkynes. Because what is the functional group for alkynes? So alkenes is a carbon-carbon double bond, and correct, Abigail, alkynes have the triple bond. So again, each carbon will have 4 bonds, but in an alkyne it's only bonded to 2 atoms, and in an alkene it's bonded to 3 atoms. So we can still add more atoms. And when we add more atoms, it's called an addition reaction. Okay, so can you see here this carbon atom in red? It's bonded to 1, 2 hydrogens and another carbon. This carbon over here is bonded to 2 carbons and a hydrogen. So we can add another atom to the 2 carbons in red. Can we add another atom to the carbon in black? To the black carbon? No, because it's saturated. It's already got 4 bonds with 4 atoms attached to it. These are what we call unsaturated. So we can add more. So that's the first type, addition. Then we can have the opposite, is where we've got, say, a carbon with 4 bonds bonded to 4 atoms, and then we remove an atom. So that's what we call an elimination. So if, for instance, I had this set up over here, who would like to give the name of that compound? Just trying to bring back what we did a term ago. I know you've had the holidays. First of all, what is the functional group? Okay, Nicholas is typing, and if you want to give the name Nicholas, it's fine, you carry on. But for anybody else, think of what is the functional group? 2-chloropropane, correct Abigail, great. So we've got the chlorine, so it's a haloalkane, and that's bonded to this second carbon, that's why it's 2-chloropropane. 3 carbons in a row, so propane, because we've only got single bonds between carbons and hydrogens, and the chloro is on the second one. Right, if I remove this chlorine and an adjacent hydrogen, so in other words a hydrogen from an adjacent carbon, so this chlorine is bonded onto the red carbon, and I could either take this hydrogen off or that one, actually any of these hydrogens actually, and then I would form propene. Because even if I removed this hydrogen, if you can twist this in your mind, if I remove this hydrogen and that chlorine, so this top hydrogen, that chlorine, the double bond forms here. But is that going to be a different atom to this one, or a different molecule, sorry, to this one, alkene up here, or will it be the same if I form the double bond here? So see Abigail's it'll be the same. So for the rest of you, if you're not sure, you've got to, it really helps to build these things in 3D. In your chemistry kits, you should have a pack of toothpicks and plasticine. There's not very much plasticine in there, I must say. You're welcome to make your own Play-Doh and just build molecules, because if you can see it in 3D, it's just so much easier. You know, when I say you're forming the same compound, because you just have to turn it around. Remember, to change from one isomer to another, you have to actually physically break a bond and remake it elsewhere. If I just have to turn it, then it's the same molecule. So if I go from this compound to that, it's an elimination, because I have removed two atoms. I've removed an atom or group of atoms from two different carbon atoms, or two adjacent carbon atoms. I can't remove this hydrogen and that hydrogen. Why not? Why can't I remove this blue hydrogen down here and that blue hydrogen down there? Where could a double bond form if I did that? Could it form anywhere? Okay, nobody's too sure. Okay, Shania, yeah, okay, yep. You're right, Shania. The double bond can't form anywhere, because what will happen is this yellow carbon will have 3 atoms bonded to it, and remember we need 4 bonds with 3 atoms, and this one will have, you know, 3 atoms. If I remove this hydrogen down there, so I've got that one, and this carbon, so I've got 3 atoms, but where will the 4th bond go for the 2 yellow atoms? It can't go to this red one, because the red one has already got 4 and it cannot go up to 5. So it always has to be adjacent carbon atoms. Spell it out when you're writing, when you're explaining why something is an elimination. You know, say that the atoms or groups of atoms must be removed from adjacent carbon atoms. Do you know what I mean when I say adjacent? So adjacent, good, just simply means next to each other. Okay, right, so that's addition, elimination. The next one is substitution. So substitution is when you replace one thing with another. Okay, you substitute one thing with another, same thing. So if I went from 2-chloro propane to, who would like to have a go at the name of this compound? And it's not 2-hydroxypropane, I can tell you that. So who would like to have a go at naming that compound? Okay, Abigail, how many carbons before it can form a ring? You can get a ring formed with using just 3 carbons, but they're quite explosive, because you can imagine the strain that those carbons are under. Because remember, each carbon will want to form 4 bonds, so 4 areas of negative charge. Thinking of your 2.4 standard we did, bond angles will be 109 degrees. Now can you imagine if I'm trying to make a triangle, the bond angle is pushed from 109 to 60. So there's a lot of repulsion going on there, and it's just hanging in there. So you can push it with 3, but they're very, very reactive. So it's the more stable ones are 6. You can get 5 as well, but the 6. So your sugars, your glucoses, and all that sort of thing, they're all based on rings of 6 carbon atoms. And Abigail, correct with the name propanol, except you didn't tell me where that OH is, because the OH can be on 2 different positions for propanol. It can either be on the first carbon, or it could be on the second carbon. So you have to tell me which one. Yep, propan-2-ol, correct. Okay, so for the rest of you as well, just when you asked for a name of a compound, just have a look and say, if you just say propanol, if there's no other way you can draw that set of atoms, then you're fine. But with propanol, I could have put the OH on 2 different carbons, so propan-1-ol or propan-2-ol. So I have to specify the number. Right, so I can substitute by going from the chloro to the alcohol, or the alcohol to the chloro. Oxidation. Now, who's done redox? The 2071, or you may have done it in school, the redox chemistry. So quite a few of you are typing. Right, great. So now I'm going to say, what is oxidation? So if my substance is being oxidized, what's happened to it? Now this is from your redox chemistry, not what I've said over here. We'll get back to this again. Its oxidation number has increased. That's right, it's become more positive because it has lost electrons. Now that is still happening here with organic. So we're still having a change in oxidation number. The problem with organic is that the oxidation number of some carbon atoms change, and of others it doesn't. So for instance, if I oxidize this carbon atom, then the oxidation number will change, but the yellow carbons will still stay the same. So we don't really try and work out oxidation numbers for oxidation. Just as a rule of thumb, for organic chemistry, if I'm adding oxygen or removing hydrogen, I'm oxidizing it, pretty much. So we'll go through and you'll see that. Okay, and then the final one you need to know is acid-base. So I think you all know what happens with the acid-base reaction if you've done it in level 1. Otherwise, if you've forgotten about that, you will do it in the 2.6 standard. But would anybody like to say what an acid-base reaction is? If you've done the titration, you would have come across an acid-base reaction there. Okay, I saw guest was typing, but stop now. Okay, so it's pretty much where one substance, the acid, is donating a proton, and the other substance, the base, is accepting that proton to form water. And just hopefully everything goes to neutral. Okay, so we'll look at that because you will be reacting an acid with a base. So that'll be my next question as recall from term 2. What functional group is an acid? And this is an easy one because the functional group has acid in the name. So if we go through the ones you had to know alkanes, alkenes, alkynes, alcohols, haloalkanes. Great, you've got it there. The carboxylic acids and the amines. So great, the carboxylic acids are acids, so they're obviously going to be doing acid-base reactions. Now, of the ones, I think there's 7 that I've listed there, which one is a base? So remember, it was the alkanes, alkenes, alkynes, alcohols, haloalkanes, amines, carboxylic acids, the amines. The amines, remember, it's got that Ni, so if you go backwards, think of nitrogen. So nitrogen has got a lone pair of electrons it can use to accept a proton. So if I react a carboxylic acid with an amine, it'll be like an acid-base reaction. Or I could react a carboxylic acid with any other base, like sodium hydrogen carbonate, like baking soda, and then I'll have, the normal acid plus carbonate gives salt plus water plus carbon dioxide gas, so I'll see fizzing. Or I could take my base, like my amine, and react it, say, with hydrochloric acid, and it'll still be an acid-base reaction. Okay, then identify the reactive site is my last tip. I think I've got one more, but that's part of your learning as well. So if you trying to, say they give you a molecule and they say they're reacting it with something, and you've now got to draw the product. A lot of students are not quite sure where to do it. So if you identify where the reaction is going to happen, then it's much easier. So you look for the functional group. So if it's an alcohol, you look for the OH. If it's a haloalkane, you look for the Cl. If it's for an alkene, look for the double bond. And then you see, okay, this is not that important, but it is helpful if you're trying to work out what's reacting. This is really for the, if it's, say the alcohol, the carbon that's bonded to the OH group, the O is more electronegative, so that bond between the carbon and the oxygen, which one has got the greater share of those electrons, the carbon or the oxygen? So oxygen is more electronegative, which means by definition it's got a stronger attraction on the bonding electrons, and so oxygen will attract those bonding electrons more strongly. So is my carbon atom going to be electron rich or electron poor? It'll be electron poor. So if it's electron poor, what sort of thing is it going to attract? Something that's rich in electrons or something that's poor in electrons? In other words, is it going to attract something that's more positive, or is it going to attract something that's like an anion or something with lone pairs or something like that? Okay, so if it's electron poor, it means it's partly positive, so it's going to go for something more that's got rich in electrons, like an anion. So here's an example where I've got ethane, ethanol, and ethanoic acid. So if I look at these carbons, they bonded onto hydrogens, which is actually less electronegative. So these carbons are actually more electron rich rather than electron poor. If I go to the ethanol, this carbon is bonded onto hydrogens. So this one is electron rich, because remember, hydrogen is not attracting those electrons as strongly. But this carbon is electron poor, because, as we said just now, oxygen is grabbing more than its fair share of electrons. And then what can you say about this carbon over here? Is it even more electron poor, or is it more electron rich? More poor, because you've got two oxygens grabbing electron density from it. So this is even more positive, okay, if we go down this continuum. So what's going to, okay, I'm just highlighting the functional groups there. But if I draw things out, the oxygen there being the most electronegative is the most electron rich, and the carbon's electron poor. We always remember focusing on the carbon and how it reacts. So here it's even more positive, and the oxygens are electron rich. So alkanes don't react very much because there's nothing that's really electron rich or electron poor. It's just they're very non-polar. There's very little difference in the molecular dipole, so they don't actually react very much. They burn pretty much. With this one, Now, don't be put off by this long word. It's just make it electron rich. A nucleophile, phile means love. So nucleo is nucleus. Nucleus is positive. So nucleophile means positive loving. It's like hydrophilic and hydrophobic is whether it loves water or hates water. Nucleophile is something that loves something positive. So a nucleophile is anything like OH minus or NH3, pretty much like a base would be a nucleophile, and that will attack. So chloride can attack here as well, thinking of that substitution, and the same thing over here. So if you look for the functional group, then look for the carbon that's part of that functional group, and that is where the change is going to happen. So if I'm changing this, if I'm substituting the OH with a Cl, the Cl will add onto this carbon atom and not that one. Does that make sense? Because sometimes I find students just draw the chlorine adding to any of the carbons in the molecule. But can you see it has to be the carbon that's got at least some differentiation here. So this one's the slightly positive one, so this is the one where the reaction is going to happen. Does that make sense? Okay, we'll go through examples. Okay, then the final thing is also think of which bonds break. Sometimes you have to think of what goes and what changes, especially if you can't remember your reactions and now you're taking a stab in the dark, because there are a lot of reactions to learn. So just think, if this bond breaks here, you've got a carbon-carbon bond. There's no difference in polarity there, so it's not going to break very easily. Also, if this comes off, this methyl group, have you ever heard of CH3 minus? Methide. Has anybody heard of it? Nope. And the reason why you haven't is because it's extremely uncommon. You will only get CH3 minus under very extreme conditions because it's just so reactive. But have you heard of OH minus? Hydroxide, yes, sodium hydroxide, potassium hydroxide, calcium hydroxide. Hydroxide is common, and that's because it's not so strong. It can be a strong base, but it's not this extreme like methide. So if you're always thinking of what's going to break, what to remove and what to replace, think of, well, I've never heard of CH3 minus, but I've heard of OH minus, so it's very likely that the CO bond's going to break and my chlorine's going to come in here, and I'm going to have the OH minus coming off. So that's just, if you get given a series of reactions and you've got no idea because you can't remember the reactions, you can sort of work out logically where it's going to happen and what's going to break. Okay, this is actually should have been point number 5. We'll go over this again, but it's helpful to remember that when organic reactions happen, they don't just go from A to B. They actually go from A to B plus C plus D plus E plus F. It's a total mess actually in the laboratory. Your bodies work really well because you've got all the enzymes and your RNA and your DNA telling your body what to do, so you don't land up with an organic mess. In the laboratory, we don't have these enzymes and DNA and RNA, so you tend to get a lot of different products. You just have to learn sort of 2 different cases when we'll get what we call the major product and the minor product. So we're going to get at least 2 products, and one will form the most and one will not form as easily. Now, you don't have to know the reasons why. When you get onto university level, you'll be doing mechanisms and so on, and they'll explain why. All you have to learn is the rule and how to apply it. So, as I said, organic reactions, particularly in the laboratory, you get mixtures. Okay, so the two rules you have to learn to try and see what's the most likely result is going to be Markovnikov and Zaitsev's rules. Now, both were Russian chemists, and because the Russian alphabet is different to the English alphabet or whatever, the spelling differs. So if you've got, say, like an ESA book or any other book, chemistry book that you're also using and not just ours, you might see a different spelling. So you may see Sayseff, Saysef, okay. Markovnikov, I've seen it with double F's and so on. As long as you can sort of say Markovnikov and Zaitsev, then you, or Zaitsev, then you'll be fine. Okay, the spelling is not important. Any questions on that? Have you perhaps noticed other spellings elsewhere? Nope. Okay. Well, you may come across it if you look at other places. And I'm also spelling that out just in case in the exam they spell it a bit differently, because there are different ways, as I say, to spell it. So, what's the Markovnikov rule? The actual rule is the hydrogen adds onto the carbon atom that has the most number of hydrogen. And that's the rule you have to write down in the exam. But a way to remember it is to think the rich get richer. Okay? So the carbon atom that has the most number of hydrogens is the rich, and the hydrogen atom goes to the carbon that has the most number of hydrogens. So that carbon gets more hydrogen, so he's getting richer. So if you just think of Markovnikov, the rich gets richer, and this applies to addition reactions because we are adding. Remember, if we're adding hydrogen, we've got to have an addition reaction. So as an example here, I've got a yellow carbon and a red carbon, and I'm only looking at those two because that's where the double bond is. So my hydrogen that comes in can only go to one of these carbons. Now I'm actually forming an alcohol by adding water, so H2O. So I'm adding an H and I'm adding an OH. So where is the hydrogen going to go? To the yellow carbon or to the red carbon? So think of which one has the most number of hydrogens, and that's the one the H is going to go to. The yellow one, because the yellow has got two hydrogens attached to it. The red carbon's only got one hydrogen attached to it. So this is the rich carbon, so it's going to get richer. And okay, I've highlighted it there, sorry there. So this will be what we call the major product. Most of the hydrogen is going to add on to the yellow carbon, but there will be some hydrogen going on to the red carbon. As I say, all organic chemistry tends to form a bit of a mess unless you've got the enzymes and so on. But you can control it to some extent, and this is one of them. Okay, so the H, you'll notice, is added onto the yellow carbon, and the OH is added onto the red carbon, but you will get a bit of the other one. So Markovnikov applies to addition reactions. Think of the rich gets richer, but please don't use that in the exam. Say the hydrogen atom, or the incoming hydrogen atom, adds onto the carbon that has the most, carbon of the double bond that has the most number of hydrogen atoms. Then we have the Zaitsev's rule, which is the poor get poorer, as the mnemonic to remember. So what happens here is, this is for what sort of reaction? An elimination, an addition, or a substitution? What do you think? So thinking of the poor gets poorer, so something is losing, so it must be elimination. We must be removing. So well done, you two. So the carbon atom that has the least number of hydrogen atoms is going to lose its hydrogen. Okay, and the one that has more of it is going to keep its hydrogens. So using the same example again, except of course I can't use an alkene now because I've got to use an elimination. So I've now used this substance and I'm going back to form the alkene again. But my OH is over there, so I can either now, okay, so remember what I said about looking for the reactive site? So where is that double bond going to form? We know it's got to form around the red carbon. So is it going to form between the red and the blue one? Or is it going to form between the red and the yellow one? So the adjacent hydrogen, am I going to remove a blue hydrogen, or am I going to remove a hydrogen from this yellow carbon? So think of the poor gets poorer. Which one of the blue and the yellow, well done, you're already there, Abigail. The blue one has got only 2 hydrogen atoms, the yellow one has got 3 hydrogen atoms. So the poor gets poorer, the carbon with the least number of hydrogen atoms loses a hydrogen. So I'm going to form as my major product the double bond between this carbon, the blue carbon, and the red carbon. Okay, so that's going to be my major product. Okay, that's going to be my minor product. So can you see this? The double bond is between the first and second carbon, is the minor product, and here the major product is where the double bond is between the second and third carbon. Now, also going back to what we did last term, the moment you see a double bond that's not terminal, by terminal I mean on the end. So this one's on the end, it's on the first carbon, between the first and second carbon. This cannot form geometric isomers, because remember with geometric isomers I need a double bond and the 2 groups on each carbon of the double bond must be different. So that group is different to the hydrogen, but can you see I've got a hydrogen on this one and a hydrogen on that one. So I cannot get the cis and trans isomers for this minor product. Can I get cis and trans or geometric isomers for this major product? Yes, because I've got 2 different groups on the blue carbon and I've got 2 different groups on the red carbon. So I can get cis and trans. So when you're doing this and you're asked what products are being formed, for excellence they are going to be looking at, did you recognize that you can also form not just this particular sort of, if that was a CH2, CH3, so in other words, 2 propene, sorry, 2 pentene, but you could form the cis version and the trans version for merit and achieved. As long as you know the major and the minor product, then you're fine. Okay, so bear that in mind. Okay, how do you know if the cis or trans is? Okay, the trans in the laboratory will always be more common. And the reason being is because of repulsion again. It's always to do with energy and repulsion. So this big group has got a lot of electrons around it. Okay, that's quite a big group with a lot of electrons around it. So the bigger the groups, the more tension there's going to be between them, the more repulsion. So it'll try and come as far away as possible. So trans will always be more common than cis in a laboratory. In your body, it's the other way around, because your body is run by enzymes and, as I say, all proteins and that sort of thing. So if you had the methyl down here and that ethyl up there, they're on opposite sides, they don't repel as much. Okay, now, what I've also got here is, did you notice the reaction conditions? Okay, let me just ask Abigail, answer here. Also, what happens if all 4 parts are different? How do you know if it's cis or trans? Okay, hopefully they'll always give you 2 that are the same, like 2 hydrogens or 2 methyls or something like that. But normally the 2 biggest groups. So if this was an ethyl and a methyl, and if they were on the same side. If it's Or if you had an ethyl and a propyl, so say it was an ethyl and a methyl over here, then it'll have to be ethyl to propyl sort of style. Those are the bigger groups. And the methyl and the hydrogen would be the smallest. But they shouldn't actually do that to you, because that's another terminology which we don't have to know now. But it's another system of naming. So you should always have two things that are the same. And I hope they're always nice to you. Okay, right. Let me actually go back. Did you notice the reaction conditions? If you just said water, or if you just said conch sulfuric acid, you wouldn't be marked correct if you had to write the reaction conditions in. Because do you notice how similar this is to that? Okay? But they do two totally different reactions. So make sure you write down as much detail as possible. Say whether it's concentrated or not. Say whether it's aqueous or not, whether they've added water. Say whether it's alcoholic, because some of the reactions you'll learn are done in alcohol rather than water, because if you did it in water you could get the wrong reaction. So just be careful of that. Okay, reactions of alkanes. So we've got about 10 minutes left, so we'll just quickly deal with the reactions of the alkanes. There are two reactions you have to know, and basically they don't do much. So what I'm trying to show there, alkanes burn. So even if you in the Arctic where methane gas has been trapped, let's get back there and I'll just stop it. Get there. Oh well, you'll see that. It burns. So that is the major thing where any alkane will react with oxygen, and if it's complete combustion, what are the two products formed? Does anybody know? If you say that the fuel standard last year, you probably know CO2 and water. Correct. That's for complete combustion. You know this is not complete combustion actually, because you see a yellow flame. The moment you see a yellow flame, you know that carbon is being produced, because what's happening is the carbon is glowing and that causes that yellow light. If you had complete combustion, what would be the color of the flame? Blue. Correct. Okay. It'll be nearly invisible. So if you do a Bunsen burner that's given lots of oxygen, so it's complete combustion, it nearly looks invisible. So we often call the yellow flame a safety flame, because you can actually see it. A blue flame you can't see, and you can then burn something by mistake. Okay, so here are the 4 reactions you have to know and the 2 tests for alkenes. And there is one more that you have to do, which is to form polymers, but I'm going to do that in another lesson. So just bear in mind there is one more reaction you have to know. So what are the 4 reactions? And you can have fun saying this 10 times fast. Hydrogenation. So hydrogenation is when we add hydrogen. So I think that's fairly simple. Hydrogenation, adding hydrogen. Do you notice the conditions? H2 with PT, platinum. The platinum is the catalyst. Because remember what I said about the reactive site. Alkenes aren't that reactive. They're electron rich, but they're not going to attract hydrogen gas very easily, so we need something just to help the reaction along, and so that's why we have the catalyst of platinum. Your books might also have nickel in, but you only have to know platinum for the exam, just in case, because I know some books that first go out with nickel in as well. So if you see nickel in your books, it's still correct, and they'll mark it correct, but you only need to know platinum, not platinum or nickel. So that's the first reaction, hydrogenation. The next one is halogenation. So halogenation is when you're adding a halogen. So a halogen could be Cl2, Br2, I2, or F2. Okay, do you think that's pretty straightforward? So By adding Br2, I'm adding a Br to each carbon of the double bond. If I used F2, I'd be adding a fluorine to each carbon of the double bond, and so on. Does that make sense? For the halogenation? Yep, okay. Now I've highlighted here Br2 because we use that also as a test for an alkene, because bromine is a nice browny reddy color. So if there's a color change, then we know we've got an alkene, because bromine is that browny reddy color and this is colorless. So if we start off with something colorless, we add something that's browny red. If it quickly goes to something colorless, we know we had an alkene to start off with. So hydrogenation, halogenation. Hydration. So what do you think hydration is? If you hydrate yourself, you're drinking water, aren't you? So it's adding water. So hydrogenation, halogenation, hydration. So can you see there was my double bond. What does water consist of? H and OH. So H goes on and OH goes on. Okay. And notice I've applied the Markovnikov rule. So this carbon on the outside that has more hydrogens got the hydrogen. The other one is hydrohalogenation, where I'm adding now not water and a halogen, but I'm adding a hydrogen and a halogen. So HBr, HCl, something like that. So if I was using HCl, then the Br would be a Cl. Okay, I know some students will they've learned this off by heart and they put a Br in even if the reagent was an HCl. So just look carefully, what is the halogen that's going to add on, and then the hydrogen is the other one. So those are your 4 reactions: hydrogenation, halogenation, hydration, hydrohalogenation. And you just need to learn the reaction conditions. So water and conch sulfuric acid. Notice any addition reaction has Markovnikov rule that you've got to think of. If you're adding 2 different things, like a hydrogen and an OH, or a hydrogen and a Cl or something, will I have to worry about Markovnikov for a halogenation or a hydrogenation? No, quite correct. Okay, because I'm adding the same group to each carbon. So, you know, a Br adds on there and a Br adds on there, so it doesn't apply. Then, as I say, there are 2 tests, and so we're going to show it here, and I'm just going to bring it up. Okay, this is an alkane. So remember, alkanes don't undergo this halogenation. Well, it does undergo a halogenation reaction, and it needs UV light, and it's a lot slower. So you can, if you leave this brown bromine, it will eventually go colorless. Because as I say, it does do halogenation as well, but it's slow, and you normally need UV light as a catalyst. But if we put it into the alkene, so can you see how instantly that brown color goes? So that is the test for an alkene, where the reddish-brown bromine decolorizes immediately. An alkane, with time, will get paler and paler and paler until it disappears. Any organic compound actually will. Okay, right. This one here, they're doing the same thing, but I want to show the permanganate. Now, remember with redox, when you did permanganate as an oxidizing agent, and then it decolorized. Do you remember the purple permanganate turned colorless because you formed the Mn2 plus ion? Does that sound familiar? Yep, okay. Now that happened because your permanganate was acidified. So if you have it in an acidic solution, your permanganate goes to the Mn2 plus. If you don't, if you've got it in a neutral solution, it forms actually not Mn2 plus, it forms MnO2, which is a brown compound. So if I just move this on a bit, because I just want to show this, okay, he's just added the alkene in there, the cyclohexene, and he's going to shake it, and notice the color change. Okay, the alkane didn't do anything, but it's gone that brown color. Now that brown color looks very similar to that bromine over there. It's not bromine, it's your MnO2. So the permanganate is decolorized. If we had acid, it would have gone to the colorless. Okay, so let's go over those again. So addition, what is added to each of the double bonds? So for halogenation, you're adding Br2 as a reactant, and so a Br of each atom goes to each carbon. Okay, so we're going to get that. So that'll be 1, 2 dibromopropane, if you had to give the name. Here, hydrogenation, you're adding a hydrogen to each carbon of the double bond, so it's just going to be propane. With my permanganate test, what's happening? I'm adding actually, it is an oxidation, because I hope you know that permanganate is an oxidant, and we're adding oxygen. We actually, I think I should have gone back there very quick there. When I add permanganate and I'm oxidizing, so can you see the purple? It is an addition reaction, so that won't be marked wrong, but it's predominantly an oxidation reaction because I've added the OH. Like this I've made blue, but you've actually also, it's a type of oxidation, but this is your main oxidation reaction, adding 2 OH groups with my permanganate. So just showing that. So I haven't shown the permanganate one, but hydration, I'm adding HOH, and remember Markovnikov, the H adds to the carbon that's got lots of H's, and hydrohalogenation, again Markovnikov, and the hydrogen will go to the carbon the most number of H's. Okay, now alkynes do exactly the same thing pretty much. So I'm not going to do our alkynes separately, but pretty much everything alkenes do, alkynes do. Alkenes and alkynes also burn, but they don't burn as completely as the alkanes, so you get very yellow flames. In fact, your miner's torch that they had down in the old coal mines, they burnt ethine, acetylene. Have you heard of the acetylene lamp? Has anybody, I think they have the acetylene lamp sort of in one of the history museums down on South Island. So the acetylene lamp is ethine, and it burns with a very, very yellow flame because it's such incomplete combustion. You form lots of carbon, so it's quite a bright yellow flame, so you can use it. Okay, so let's practice again. So for hydration, to do that reaction, is it 1, 2, 3, 4, 5, or 6 for hydration? What's the correct answer? 1, 2, 3, 4, 5, 6. If I want to have a hydration reaction, what? Okay, okay, 4 is correct because hydration, hydrate, think of water. Okay, so that is the correct one. Abigail, we'll get onto that one, but think of what this element is, and then that will help you. Halogenation. Which one is an example of halogenation? Number 2. Okay. Br2, F2, Cl2. Okay. Hydrohalogenation. So I'm adding a halogen and I'm adding hydro, but this case it's not hydration, it's hydrogen. Yes. Okay. that's right. So it's quite confusing because they all start with H. So, yep. Now, you did say number 6, and that's correct as well. So if you chose HCl or HBr, both of them are correct for halogenation. Hydrogenation. If I wanted to have an alkene there, it's number 1. So hydrogen you're adding. Which reagent do I need if I'm doing the test where the brown color fades? Okay, number 2. And the last one is the permanganate. Now I've got the acidified permanganate because that goes to a colorless solution. If you didn't acidify it, the purple would go to that light brown as you saw. Both are correct, both you can use as tests, although the standard does specify the acidified permanganate. I just couldn't find a video that showed that, and that's why I used the non-acidified one. Okay, we're pretty much on time, and because now we're going to go into alcohols and haloalkanes and amines. So, any questions before we finish? Okay, so next week we're going to be doing the other reactions, and then perhaps one more just to go through past papers so you sort of know what to write, and also we need to do polymers as well. And then we're done, and then we can go on to the third and final standard, exam standard. Right. Goodbye. Bye.